Alright, so this is another video in our series on shear and moment diagrams, and here we have a beam that's simply supported with a uniform load of 200 pounds per foot that doesn't go all the way to the end, so it makes it non-symmetric, and that's okay. What I did here is I kind of went ahead and just to save a little bit of time, I went ahead and solved for the reaction. So if you want more information on what that looks like, I'll just give you the equations here, and here they are. Wouldn't it be nice if they could just appear like that on your test and everything would be, perfect? But, all we did here is we took the resultant force, this resultant, multiplied it by, 8 over 2, or the resultant location, right? So this is 8 over 2. This is our, 4 feet essentially where this resultant acts. And we get, that has to be balanced by a moment caused by By, By times 10. And we end up with 640 pounds. When we do some of the forces in the Y direction, we can solve for AY is 960. All right, so once we have that information, we can come and we can go ahead and draw our shear diagram. So I'm just going to move this up a little bit, and what we do here is next what we're going to say is, anywhere the force goes up, our shear diagram is going to go up. Anywhere that the force goes down, our shear diagram is going to go down. So we'll just start here and we'll go up, we'll go up to 960. So if each one of these is maybe 250, 250, 500, 750, a little bit below 1,000. So we're going to call this 960, pounds. And we have the units over here, so I'm just going to leave it at that. So when we draw this in, we draw a line connecting it. So our shear, instantaneously jumps right to 960 based on our support reaction at AY, right? But you'll notice as we start coming over, for every foot that we come over, we're going to drop 200 pounds per foot. So this 200 is going to start pushing our shear back down. So if we start at 960, we're going to come to 760. And then from 760, we'll go to like 560. And you'll see that a line's going to start forming here that has a slope that's going down at 200 pounds per foot. So let's draw that line in. And, by coming down 1,600 pounds, or at a value, on this side here, we're going to end at a value of minus 640 pounds, right? So this distance here, right, from this point here all the way up to like this point here, right, this distance is gonna basically be our 200 pounds per foot times 8 feet, which equals 1,600 pounds, right? And that's the total drop from this point down to our point where we hit the end of the the end of the uniform load, right? And then the cool thing is, as we keep going kind of from left to right, you'll notice there's no load, and no load means no change in shear. So what we're going to do now is we're just going to finish that line. And that line is just a straight line across, and we're good. And then we're going to draw a line up, and that will close our diagram. So now, since our diagram's closed, what we can do is we can come back and we can shade this in. And one thing to remember, right, is after we look at this, we can look at the slope of this line. For every foot that we come over, right, we're going to drop 200 pounds, right? So that's the slope of this line. This line has a zero load, zero slope. Okay, and that's good. So that's our complete shear diagrams. There's our shear, and we've gone through, we solved for our reactions, we drew our shear diagram, and what we're going to do next is we're going to go to our moment diagrams, right? So to do our moment diagram, I'm just going to make a little bit more room here. What we want to do is we need to draw, or we need to find some areas, right? So we need to find areas of this of this shear diagram. So what I'm going to do is I'm going to label this area 1, and what I like to do is anytime I can, I like to break this up into triangles and rectangles. So this is going to be area 2, and this will be area 3, right? So we have two separate areas here, because I like to find moment at any any point where we have some change in shear or change in something. So I'm going to call this maybe point 0, this point 1, this point 2, and this point 3 when we're looking at moment, right? So what we want to do is we just want to go through and find those areas to do our moment diagram. So area 1 is just a triangle, right? So 1/2 base. Right? This is where we don't know what this base is, where we haven't solved for it yet. We need to come and we need to solve for that distance. And to solve for that distance, right, I'm just going to drop a line down here and say, this distance here I'm just going to call, x1. If we come from, this point here all the way over, I'm going to call this x1. And really what we're going to say is, well, x1 is just going to equal the height of the shear divided by the slope of this line, or divided by the uniform load. And that will get us back down to 0. So that'll give us, how far this distance is. And when we do that, when we take our shear, which is 960, pounds, and divide it by 200 pounds per foot, what we end up with is 4.8 feet. So we know this distance, x1, all the way to the point where the shear goes to 0 is going to be 4.8 feet. So that's cool, because now when we look at our base, we know our base is 4.8 feet. And our height is going to be 960 pounds, right? So this is just an area formula of a triangle 1/2 base times height, right? And when we do that out, we get a value of 2,304 foot-pounds. Okay, so that's the value of area 1. And then we can just come here and we can do, well, what's area 2? Well, area 2 is just, again, going to equal 1/2 base times height. But in this case, right, what's our base? Well, our base is going to be the remainder, right? So I'm going to call this, x2. And what's x2? Well, x2 is just this whole distance. So if this whole distance is 8 feet, what do we know? Well, x2 has to equal 8 feet, minus x1. So x2 has to equal 3.2 feet. So that's our new base, so 3.2 feet. Our new height is minus 640 pounds, and that minus sign is important because it means that we're going to have a negative area here that's going to push our moment diagram down. So when we do that out, I think we get, minus 1024 foot-pounds here. And then we can come and find our last area. So our last area, area 3, this is an easier one because it's a rectangle and we know the distance, right? We know this distance here is 2 feet. So what does that mean? That's our, rectangle is a base times height. And what do we have? We have 2 feet times minus 640, pounds. And what we get here is, minus 1280 foot-pounds. Okay, so those are all our areas, and when we go to draw our moment diagram, all we're going to do is we're going to add up left to right our areas to get our moments, right? So the moment at point O, again, if we remember, this is a simply supported beam and there's no applied moment at the end. Our moment at the end of a pin here, at the end of a beam at a pin with no applied moment is always going to be 0. So we'll start at 0, and what I'll just write in here is, well, we know that what? M0 has to be 0. Okay, it's the end of a simply supported beam with no applied moment. Okay, so that's hopefully an easy one. We'll just draw that in, we'll call that 0. All right, and then we're going to start going up. So we know that M1 is going to equal A1. Okay, so what's this? It's plus 2304 foot-pounds. Okay, so we can come over here, we can draw that in. So, maybe each of these is 500, and I'll come up to, 2304 foot-pounds. Okay, and then let's go to M2. Well, M2 is going to be what? Well, we know it's going to be, M1 plus A2, right? So we're just, again, adding all the areas. We go from left to right, A1 plus A2, or M1 plus A2 in this case, because M1 equals A1. All right, and what we get is just 2304 foot-pounds minus 1024 foot-pounds, and that is going to equal 1280 foot-pounds when we do it out. Okay, and so what we'll do is we'll plot that point out here. So here's 1,000. So we're going to say 1280 is going to be somewhere around here, and we'll label that 1280 on the graph as well. Okay, and then when we look at M3, right, what are we going to say? Well, M3 is going to be, this is the moment at point 3. What are we going to say? Well, this is M2 plus A3, and what do we get? Well, we get 1280 foot-pounds, minus 1280 foot-pounds, and you can see that goes back to 0, which is good. It means our moment diagram closed, and there's a good chance we did this right. Okay, so the next question comes, and we have the dots, we have the numbers, now we're playing connect the dots, but we got to figure out how to connect the dots. And one of the things that I look for is I know that the height of the shear diagram is equal to the slope of the moment diagram. So I look for easy spots, right? And the easiest spot I can think of is, well, this is a 0 point. The height of the shear diagram here is 0 at point 1, right? 0. You can't get any easier than that. The slope of 0 is going to be horizontal. So what that means is at this point, our slope is going to be horizontal, okay? So that's going to be our slope. And on to the left of it, we're going to have a positive slope, so this is going to be increasing. On the right of it, this is going to be a negative slope, it's going to be decreasing, but it's not going to be a straight line, right? So if this is, right, our 0 slope here, just a 0 slope, what we know is we have a pretty big positive slope right at the start, and a pretty, decent sized negative slope at the end. So how do we, what does that sort of beg to show us? It begs for a curve, right? Again, if we, come halfway in between, we have a lesser shear value here, so our slope's going to be a little less positive. Here a little less negative. And you can see, hopefully, that this is going to connect with some sort of parabola. So not a perfect curve, but I got it pretty close. All right, and it looks decent. All right, so what we're going to do next is we're going to go ahead and we're going to do this last section. In this last section, we have a straight line, a horizontal line here for the shear. So that means we're going to have a constantly sloping moment diagram of minus 640 pounds per foot. So what that looks like is we're going to draw a line essentially that connects this spot to this spot. Right, and there's our line. And if you're ever, in doubt, what I would do is I would just write in parabola, so it's really obvious that you know what you're doing, because you want to get all the points you can. You want to get these answers right on, the FE if you're taking that. And here we have lines, that come along these lines. Okay, so this is a line, this is a parabola. We have our points, and we can shade our diagram in. And once it's shaded in, we can really go back also and say, well, now we know the maximum shear, right, that this beam's going to experience is going to be this 960 pounds at the, basically at the reaction at A. And the maximum moment is going to be this 2304, 2304 pounds, or foot-pounds, I should say, at a distance, right, at a distance of 4.8 feet from A. Right, and that becomes important just in the sense of where that where that location is, where it occurs, and again that corresponds, if you're wondering where the 4.8 comes from, that corresponds with this x1. Okay, so we could drop a line there as well, but that's where that maximum moment is going to occur. So there we have it, and I hope this example is helpful. If it is, feel free to click the like. If not, if you have questions, feel free to drop a comment, and otherwise, until next time, keep working hard and moving onward and upward.